All right, welcome. If you've ever stared at the modern Java world and felt like you're looking at a crazy, tangled subway map, you are definitely not alone. Today, we're going to draw a clear path through all of it. We're going to go from one single line of code all the way to a huge application running out there in the cloud. Let's dive right in. This is really the big question, isn't it? How do you get from a simple "Hello World" to a massive service that millions of people might use every single day? Well, we're going to follow that exact journey. We'll start with the absolute basics, the DNA of our code, and see how each new layer we add, frameworks, databases, architecture, solves a new, bigger problem. So our journey has to start with the core building block, Java itself. Its big promise has always been write once, run anywhere. And that's not some kind of marketing slogan. It's the whole point. It's all thanks to something called the Java Virtual Machine, or the JVM. This thing is the magic piece of software that lets the exact same Java code you write run perfectly on a Windows machine, a Linux server, a Mac, you name it. Now, from the very beginning, Java makes you get organized. Think of your code like a giant digital filing cabinet. The project, that's the whole cabinet. Each package is like a separate drawer, for keeping related things together. Inside those drawers, you have classes. Those are the individual file folders. And then finally, inside the folders are the actual pages, your variables and methods, the data and the instructions. This structure is absolutely what keeps a huge application from turning into total chaos.
Okay, let's zoom in a little bit, right to those variables. Where you decide to declare a variable basically determines its entire life. How long does it exist? Who gets to see it? And this isn't just, some academic exercise. Understanding whether your data lives in the heap, or the stack, or somewhere else, that's the key to writing code that's efficient, that's bug-free, and that doesn't eat up all your memory.
Encapsulation. This is all about control. The best way to think about it? It's like a bank vault. Your account balance? That's private data, and it's locked away inside. You can't just walk up and scribble a new number on the ledger. No way. Instead, you have to go through a bank teller. These are the public methods like deposit or withdraw. This whole process protects the data from getting corrupted and makes sure every single change is done the right way.
Inheritance is basically Java's built-in "don't reinvent the wheel" feature. It's super powerful. You can start with a general blueprint, let's say a vehicle class. Then you can create more specific versions like a car or a motorcycle that extend from vehicle. Instantly, they get all the normal vehicle features, wheels, an engine, whatever. All you have to do is add the details that make a car, or a motorcycle. It's a brilliant way to reuse code.
And then there's polymorphism, which gives our code some amazing flexibility. The word literally means many forms, and it lets a single action have totally different results depending on the situation. For example, both a car and a motorcycle might have a start engine method, but how they do it is completely different, right? That's called method overriding. It lets us write general, clean code that can handle all sorts of different objects without getting messy.
Okay, so we've got our Java building blocks. We have classes, we have inheritance, we have polymorphism. That's great. But a pile of bricks doesn't just magically become a house. So how do we actually assemble all these little pieces into a huge, powerful application that can run a business without it turning into a tangled spaghetti monster of code? And this is where the Spring Framework enters the picture. It gives us the blueprint for the house. And its secret weapon is something called inversion of control, or IOC. See, without it, every part of your code is responsible for finding and creating every other part it needs. It's a nightmare with IOC. We just tell Spring what we need, and the Spring container acts like a master builder, assembling and wiring everything up for us. It lets us focus on what our app should do, not all the boring plumbing underneath. So what does this look like in action? Let's follow a single web request. First, it hits something called the dispatcher servlet. Think of this as the front door to our application. This dispatcher then asks the handler mapping, hey, who's in charge of this kind of request? It points to a specific controller, which is where the real work happens. The controller does its thing, packages up the data and a view name, and then the view resolver figures out how to display it, like which web page to show. It's like a super clean, predictable assembly line for every single click a user makes.
Right. Our app is running, but it has no memory. It forgets everything as soon as you turn it off. It needs a database. We talk to databases using a language called SQL. which is really split into two parts. You've got DDL, the data definition language. That's for building the structure, creating the tables, altering them. Then you've got DML, the data manipulation language. That's for actually working with the data inside those tables.
But here's where we hit a really big wall. Our application thinks in terms of Java objects, with fields and methods and complex relationships. But our database, it thinks in terms of simple, flat tables with rows and columns. They basically speak different languages. And this headache has a name. It's called the Object Relational Impedance Mismatch.
And the solution to this problem is Hibernate. It's an Object Relational Mapping Framework, or ORM. Honestly, the best way to think of it is as a powerful universal translator. It just sits there right between our Java code and the database, and it automatically handles all that tedious work of converting our Java objects into database rows and then back again. We get to work with our nice, clean objects, and Hibernate makes sure the database stays perfectly in sync. It's a lifesaver.
So Hibernate carefully manages the entire life journey of every piece of data. An object starts out as transient. That just means it exists only in your app's memory. The database has no idea it exists. The second you tell Hibernate to save it, its state flips to persistent. Now it's connected to the database, and Hibernate is watching it, tracking every single change. And when you're done with it, it becomes detached. It's no longer being watched, but its record is still saved in the database. Understanding this life cycle is totally key to using an ORM right.
This slide shows a classic developer dilemma. It's like the tortoise and the hare. When you need to fetch some data, using GET is like the hare. It's eager. It sprints to the database immediately to get what you ask for. But you might be fetching data you don't even end up using. On the other hand, LOAD is the tortoise. It's lazy. It just gives you a placeholder, a little proxy, and it only actually goes to the database when you try to use the data. It's way more efficient, but you better be sure that data actually exists when you finally ask for it.
Okay, so far, everything we've built has been one single giant application, what we call a monolith. And look, monoliths are simple to get started with. But as they grow, they become these huge beasts that are hard to update and even harder to scale. If one small part fails, the whole thing can crash. The modern approach is to break it up into microservices. Think of it as a city of smaller, independent applications that all work together.
So if our application is now a city, how does anyone find anything? That's the job of the API Gateway. It is the single front door for all traffic coming from the outside world. It acts like a bouncer, checking IDs and authenticating requests, and it's also the receptionist, looking at each request and routing it to the exact microservice inside the city that can handle it. But wait, how does the API Gateway even know where all the other services are? Well, it looks them up in the service registry, and a popular one is called Eureka. You can just think of this as the city's phone book. When a new service starts up, it adds its address to the book. When another service needs to talk to it, it just asks the registry, hey, what's the current address for the payment service? This allows the whole city to be dynamic, with services coming and going all the time.
Okay, what happens when one of our services gets really popular? Let's say our user service is getting hammered with requests. Well, we can't just make that one service bigger. Instead, we run multiple copies of it. And the load balancer is the traffic cop that stands in front of them all. It takes all the incoming requests for the user service and just distributes them evenly across all the available copies. This ensures no single one gets overloaded, and our whole application stays fast and responsive.
Our city is built, but how do we know every building is up to code? We test it. And a really cool way to do this is with behavior-driven development, or BDD. It basically frames tests as simple, human-readable stories. For example, given a user is logged into the shopping app, when they add an item to their cart, then the cart's total price should increase. This makes our test super clear for everyone and ensures the app actually behaves the way we expect it to.
And this brings us to the final and maybe the most critical question of all. We have built this complex, amazing distributed system. It handles user data. It's tested. It's scalable. But is it secure? All of that incredible work is completely worthless if we haven't locked the doors. How do we protect our services and, more importantly, our users?
The modern answer to that question is OAuth 2.0. You use this all the time. Think about when you see a Login with Google button on a new website. You are not giving that website your Google password, right? Of course not. Instead, you're telling Google, hey, give this app a special temporary key. It's called an access token that only gives it limited permission to do a few things. The app never ever sees your actual password. This idea, called delegated authorization, is the secure bedrock of the modern internet.
And there you have it. We've gone on a huge journey, from a single Java class all the way to a secure, scalable city of microservices living in the cloud. We've seen how every single layer, from Spring to Hibernate to an API gateway, it all solves a specific, crucial problem, allowing us to build these incredibly powerful applications. The ecosystem is vast for sure, but hopefully now you have the map. So the only question left is, what are you going to build first? Thanks for joining us.